Nice for this part. But the way it works is that we're going to leave like the last 10 or so, because you only need to know the first 30 or so to do the homework. So we're just going to kind of get to near the end and then assign the homework and call it a day. Okay? Now, why am I?
My thing's not working. Poor thing. I don't know why. Okay. I like this idea. We've been talking about how fast a reaction occurs, or how fast a reaction, what we say, proceeds from reactants to form products. That's the reaction rate. Well, we are now going to talk about how mathematically you can describe rate. So as we talk about these reaction rates, they're the same reaction rates that we talked about in part 1. And it's a mathematical relationship that actually ties in the concentrations of the reactants, not the products, the concentration of what you're starting with to the rate. Oh, that works. You know, the other day I kind of complained that with regard to induced dipole, there's so many words or so many terms, dispersion forces, induced dipole, London forces. Well, so this idea of this mathematical expression to describe rate has all these different terms. So I probably call it the rate law expression. Rate law expression. It's the equation that says how fast the reaction occurs relative to the molar concentration of the reactants. Rate law expression. Maybe I'll call it rate law expression. Rate expression, rate law equation, rate law. You get a pick. They all mean the same thing. So we're going to deal a lot with kind of this generic A plus B goes to form, those are our two reactants, A and a reactant B. Now, the little a and the little b, I think we've done this before, are the stoichiometric coefficients, okay? So A plus B goes to form some sort of product. So here we go. This is your first rate law expression, your rate law expression. The reaction rate, rate, is equal to, we'll talk more about what K means. What do the brackets mean? Remember? Molar concentration. Molar concentration of A raised to M times the molar concentration of B raised to N. Okay. We talked about the little subscript zeros before. Remember that? That means the starting. So if we're concentrating on the starting molar concentration of A, starting molar concentration of B, what you get is the rate at the beginning. What happens to reaction rates over time? They always slow down. Yep, they always slow down. We still need to talk about K, M, and N. Okay? Well, here you go. K is called the rate law constant. In general chemistry 2, we're going to have many constants. Now, this is a constant that actually is specific to the reaction that's occurring, though. It's not like the ideal gas law constant. The rate law constant is associated with that particular reaction. Okay, well, if we're going after the initial rate, then we need to have the initial molar concentration of A and B. Those will be in moles per liter, molar concentration. Now, the M and the N are called reaction orders. M is the reaction order of the reactant A. N, as in Nancy, is the reaction order for the reactant B, reaction orders. But mathematically, I just think this is so cool. I mean, science is so cool that literally we take the molar concentrations, raise them to a power. That's the reaction order. Okay? Molar concentration raised to the power times the K is going to equal to the rate, the reaction rate. That's so cool. We need to talk about how we get our reaction orders and how we get our rate law constant. We'll get there. So that power, that reaction order, then identifies, like this says, how the rate is dependent upon the molar concentration. Reaction orders, the little superscripts, the powers of A and B. or the molar concentration of your reactants. That is not necessarily the stoichiometric coefficient. And sometimes I make this one dramatic. I guess not. Blue should be dramatic if I can make anything dramatic. The reaction orders, M and N, we can only get through experimentation. Only. Clear at the end, and I almost feel like I should lower my voice because otherwise, I don't know whether to lower my voice or raise my voice. But clear at the end of Unit 1, we're going to talk about some, what we call elementary steps, kind of behind the scenes, what's going on with regard to a reaction. In that case, we can actually use what's called molecularity. In that case, we can use stoichiometric coefficients. I hesitate to say that as the reaction orders, but only in that case. Otherwise, blue, we get the M and N, we get the reaction orders for A and B through experimental work. That's it. Okay, and actually there are still different, I think we're going to talk about 3 different ways that you can get to the reaction orders from experimental data. There's kind of different nuances there. So let's again consider reactant A and reactant B going to form some sort of products. So sometimes this is kind of our out of the box sort of equation, okay? This is our template sort of. When we start to look at the data, we can actually evaluate M and N and actually K and come up with the real rate law expression, but this is kind of a template. Okay. Now, one thing to talk about, because it is a player, is this thing called the overall reaction order. Well, I talked about a reaction order for A, which is M, a reaction order for B, which is N. So the overall reaction orders, you just add M plus N. Overall reaction order is M plus N. In this case, with 2 reactants. You just add them together, overall. Well, if you raise anything to the 0 power, what do you get? 1. You totally get 1. Anything to the 0 power is 1. So it's quite possible that, and I won't draw it again, but A plus B goes to form products. You get rate is equal to the rate law constant K times the molar concentration of A raised to its reaction order times the molar concentration of B raised to its reaction order. Yeah. If you make this 0, if that's 0, then this thing is 1. And so like the slide said, if your reaction order is 0, this has no effect. Whatever you put in for the molar concentration of A, don't matter. It has no effect on your rate. No effect. Oh, it didn't say that. I guess maybe it says the next thing. The other thing is this can be positive or negative. Okay? So let's say I make it a +2. Well, that means that if I increase this, or if I monkey with this, I'm going to square it, and that's going to affect my rate. So how do I say this? If I keep increasing this, my rate's going to go up. Okay. Now, inversely, and we are going to deal with negative reaction orders, but if I put a -2 there, check this out. We are going to deal with negative reaction orders. But as I increase this, that's like the negative means it's in the denominator. As I increase this increases, this will decrease. Does that make sense? And one of the things I think I talked about the other day was increase concentration, increase rate. So actually, we're not dealing with negative reaction orders. So positive reaction orders 0 has no concentration, has no effect. They don't have to be whole numbers, okay, but they usually are. For any positive reaction order, the rate of reaction increases as the concentration increases. Negative, not so much, right? So as we get going here, we're going to focus on reaction orders of 0, which has no effect on the concentration. Reaction order where the superscripts or the reaction orders are 1 and 2, which corresponds to 0, first and second order. 0 order, first order, second order. Well, we have a little bit of we need to be dimensionally consistent. So hopefully if I were to ask you what the units of rate were, since you just kind of done some homework about that, hopefully you would say it's molar per time. Or break molar out, that's moles per liter per time. And time could be seconds or minutes or hours. Okay, that's what our units of rate are. Rate are, not rate are. So whatever units are introduced by raising molarity to this power and molarity to this power, the way I think of it, your units that are introduced by your rate constant K need to compensate for those units to come back to this for your rate. That's how I think of it. So in that case, we talked about the overall reaction order. That's m plus n, right? M plus n is equal to overall reaction order. Well, if your overall reaction order is, I can't remember what my slides say. Oh, okay. If your overall reaction order is 0, which is kind of weird, right? Okay. K needs to take on units so that your rate is equal to moles per liter per time. So you guys told me if this is 0, then basically that's 1. And so anyway, these will be moles per liter per time. Okay. Now, if it's first order, then things get a little more interesting. If it's first order, then that's going to introduce a moles per liter, 1 moles per liter here. So if we want moles per liter per time here, your K is going to be basically per time. That's it. Your K is going to be per time. If it's second order, then you have molarity squared, or mole squared per liter squared. Okay, and if you want moles per liter, you've got to basically delete one of those moles per liter per time, and it ends up like this. Do you recognize this is your way to delete one of those units of moles per liter? Inverse molarity time or liters per mole time. Yep. So we're going to be when I show you how you get your Ks, you need to kind of keep your wits about you, and the units of K make a difference. And I'll go ahead and kind of get ahead of myself a little bit. You can use the units for K to understand, if somebody gives you the rate law constant K, you can use those units to backtrack to what the overall reaction order is, or the reaction order with regard to one reactant. There's only one reactant. Okay. So rate law constant K, moles per liter per time, molar per time raised to the negative first power. They all mean the same thing. That would be for 0 order, right? 0 overall reaction order. This is for overall reaction order 1. Inverse time raised to the negative first power. This is overall reaction 2. Or basically, I kind of think of it where you have the inverse molarity, inverse time. Those are all ways to express that. You get to pick which one you want to use. So, and actually the little thought process we did here to come up with the overall reaction orders of 0, 1, and 2, you could continue that for 3, 4, 5. Okay, so here's what OpenStax does. For 0 order, and I don't really like this I don't like the 2 slashes. That kind of drives me nuts. What they're trying to do is show you what I think is a major divisor right here, moles per liter per second. Overall reaction order first, we said that's inverse time. Overall reaction second. That means your units of K need to be basically inverse molarity, which is liters per mole per time. We didn't do this one. Third would be inverse molarity squared, basically. Which is kind of, I really don't like how they did that one. What they're trying to say is liters squared per mole squared. In this case, their time was seconds squared. I'm like, that is just terrible. All right. Oh, I meant to print this out. But you're just going to have to kind of switch back and forth, maybe. So what does the little subscript 0 mean? Initial, yep. So we're going to kind of take through, do some kind of thinking through what this would look like. If our initial molar concentration of A is 0.20 molar and decreases from there, A is a reactant, okay? Oh yeah, this is kind of setting up for the next slide, which I didn't print out. Let's just say you run it again. The second trial, like is indicated by subscript 2, which I don't know, I'm not real sold on this. But the second trial, you took twice of what you took during the first trial. I think probably instead of 0, I would probably say, this is your first trial. This is how I think of it. This is your first trial. Your second trial, you're going to take twice as much. All right. And see what effect it will have on your reaction rates. So for the next slide, when we kind of think through this, we are going to have a reactant A and reactant B, and we're going to hold B constant. We're going to hold the temperature constant and everything. Okay, but B is going to be constant, but A is going to change. So our rate law expression for A reacting with B would be like this. Okay, again, B is going to stay constant. Now, we've used primes in here before, like the little tick mark, that's a prime. Here, I'm going to use it, and it's going to be, I'll write it down. The word is pseudo, meaning kind of fake. That prime is going to be called, we'll call it pseudo constant. So here's the deal, left and right. If the left is my rate law expression, if I hold this guy constant, okay, what you see here is I have balled this constant in with the K and made it what we call a pseudo constant. P-S-U-E-D-O. What a cool word. Pseudo constant. My pseudo constant K prime is equal to my K times the molar concentration of B raised to its reaction order, which is N, which that is going to be held constant. I hope that makes sense. Okay, so with that in mind, here's what the data can look like under different scenarios. So in each case, like I said a minute ago, we are going to double the concentration. So again, I'm going to call this my A1 for my first trial. This is my A2. A2 is, what we say, twice A1. We're going to see what sort of effect we can have on the rate. Now, if our reaction order is 0, then when it comes time to raising the molar concentration of A, in the first trial, which is 0.2, to the 0th power, I get 1. The second trial, if it was 0.2, now it's 0.4, raise it to the 0th power, I also get 1. This is an example where your rate, like we said before, is going to stay the same. Its reaction order of A is 0. We can double, we can triple, we can quadruple it. Your rate's not going to change if it's 0 order. Well, let's kind of think through this again. What if changing it up, different reaction,
Now your reaction order is 0, it's 1/2. Let's see what that would do. Well, we take 0.2 raised to the half power, because reaction order is 1/2, we get 0.45. We take 0.40, our second trial, raise it to its reaction order, 0.5, we get 0.63. Now, not even knowing what K or K naught is, the relative rates would be this. I can take the number 63, I have a calculator. I can take 63 and divide it by 0.63 or 63, doesn't matter, divided by 0.45 or 45. And what you'll get is 1/4. 0.63 divided by 0.45, 1.4. So it's going to go faster with twice as much. How much faster? With a reaction order of 0.5? 1.4 times faster. That's it. So we double and we got 1.4. And it's systematic. That'll always be the case. Now, I'm not as worried about the half order as I am the other two orders. So it looks like this. I think I might have told you we're going to focus on 0, 1, and 2. So let's look at first order. So on our two trials, if it's first order, we're going to raise the concentration up to the first power, which is like we get it back again, right? So the relative rates are 0.2 and 0.4. If you divide 0.4 by 0.2, you get 2. That's where this doubles comes in, okay? We're all on the same page here. So that doubles came from 0.4 divided by 0.2. Okay, that makes it double. The rate will double. When does the rate double? The rate doubles, I know it sounds like a lot of ifs, but the rate doubles if it's first order and if you double the concentration. So those two things. The last one I want to worry about is this one. What if it's second order? Well, we'll look at our molar concentrations of our two trials, 0.2 and 0.4, and we'll square them. We get 0.04. I mean, these, I don't do squares as much as I do anything else. So yeah, 0.2 raised to the second power is 0.040. 0.4 raised to the second power is 0.16. If we take 0.16 divided by 0.040, you get 4. And of course, quad meaning 4. It will increase by a factor of 4 times. When will that happen? Well, if you double the concentration and it's second order, okay, your rate will quadruple. This was 2. And this guy right here, 1.4, was, what do we say, 0.63 divided by 0.45. Anyway, all right. So this actually, and like I said, the ones I want to emphasize are 0, first, and second. We're going to actually see some data here in a minute. And it's called by inspection. Just by inspection, we can look at what influence doubling the concentration has on the reaction rate. All right. Just by inspection. So we're going to run a series of experiments, okay? All parameters, except for the concentration of one particular reactant, are held constant. We're going to measure the initial rates, and then systematically, it's kind of like being a detective. You can actually compare two trials in which only the concentration of something was changed, in this case hopefully doubled, and look at its effect on the reaction rate and to do something. So today we are going to look at the first two, and like I said, you'll have homework for the first two in part 2 homework, and then we'll come back to the graphical approach. So this one's going to be by inspection. So yeah, like I said, I wish I printed this out, but this should work. Hydrogen peroxide reacts with iodide, ion, and acidic conditions. That's where H+ comes from, to give us molecular iodine and water. So if I were to come up with the rate law expression, I kind of like to have a little, I call it the template. Rate law, okay. Rate, I'm not going to worry about initial rate, initial rate, is equal to rate law constant K. And again, it's just about the reactants. The molar concentration of the H2O2 raised to its reaction order, I'll call that M. The molar concentration of the I minus raised to the N times the molar concentration of the H plus raised to the element O. How's that? And as we work this problem, we're going to actually be filling in the reaction orders M, N, and O, and we're also going to, I'll show you how we can knock out the rate law constant K. So you're going to see on the table where it was run 4 times and strategic with regard to the molar concentration of the reactants. And the rates, initial rates, were measured for each experiment. So we're going to be able to come up with M, N, and O, the reaction orders with regard to those 3 reactants. We're going to ultimately then, we can plug them in and get the rate law expression. Sometimes I never know if the rate law expression, do you put the K in there or do you refer to the K later? But the rate law expression where we substitute in the superscripts, the reaction orders, and the value for the rate law constant K. So here are 4 trials. And again, these were not picked willy-nilly. The by inspection that you're going to be exposed to is going to be look for a doubling. So for instance, do you see where I can use 1 and 2? Notice that these were held constant. I can use 1 and 2 to get to the influence of the H2O2. Any changes I see over here were from the H2O2. Now, notice that they're both the same magnitude, 10 to the minus 6, and I can actually take 1.15, and if I double it, I get 2.30. So I'm liking that actually in doubling this concentration, do you see I see a doubling in the rate, just eyeballing it, but we can also use a calculator. Sometimes you'll need to use a calculator because it's harder to see that the doubles than you might think. But just doubling the H2O2, it doubled the rate, which we said that corresponds to a first order. So already I know what M is. See how that works? Let's see, if we focus on, again, these were, each were on strategically. So it looks like 1 and 3, if I focus on them, it looks like the thing that's changing, I'll just circle it instead of drawing dashes through it. So the thing that's changing is the I minus, and between the first and the third trial, I see that I am doubling the molar concentration of I minus, and again I see the rate doubling, so it's first order. So, and my slides are going to kind of reflect that, but that's with trial 1 and 3. Let's see, why did we run the last trial? Well, must have been a reason. To me, if I compare the first and the fourth, it looks like the only thing that's changing is the H plus. So the first and the fourth, I'm thinking that that's going to give us the H plus. So I'm doubling the H plus, and notice if I look at the rate, there's no effect. 0 order? Yeah. So, like the slides say, we're going to choose a pair where the only difference is the concentration of 1 of the 3 things. Like I said a minute ago, if you look at 1 and 2, you're going to see that doubling the H2O2 doubles the rate. Okay, which in that case, that's always going to mean that you are dealing with something that's first order. Did I skip some slides? Okay. So this is by inspection. By inspection will be doubling. Now, here in a minute,
I'm going to have to change it up because we don't always systematically double the molar concentration of things. Wish life was that easy, but it's not. We compare experiments 1 and 3 because the reason we do that is because the only thing that changed was the molar concentration of I minus, and doubling the molar concentration of I minus resulted in doubling the rate. It's almost like if you're looking at, like, well, that must mean it's second order. No, doubling the molar concentration, doubling the rate means it's first order. Just kind of like I tried to show you a minute ago. And then last but not least, for the H plus, we can look at the first and the last run. And when we doubled the H plus, there was no change in rate. That means it's zero order. So we have now filled in our M, N, and O as 1, 1, and 0, respectively. Am I going to lose my voice this week? It's a possibility. Just by inspection. So what's the overall reaction order? It is 2. So we know what the units of K are going to be. Speaking of K, we need to knock out K. So yeah, I told you I've been on this, I've taught this course for 15 years. I'm usually on the fence about this. So the rate law expression for this reaction is, notice we didn't find a value for K yet. We're going to find a value for K. But just plug in the variable K. So the rate, or the initial rate is equal to the rate law constant K times the molar concentration of H2O2. The initial molar concentration of H2O2 raised to the first power times the molar concentration of I minus raised to the first power times the initial molar concentration of H plus raised to the 0th power. So usually you won't see it written like this. Usually you'll see it written like this. Of course, the difference is 2, I guess, where notice I don't have the superscript 1. It's kind of implied. And the other thing is I don't have the molar concentration of the H plus raised to the 0th power because that's 1. Rate law expression. So I guess this is note to self that if you don't see a reactant in your rate law expression, it must be 0 order. It's going to be every reactant raised to its reaction order. Cool. So to find K, you get to pick your favorite trial, 1 of 4 trials, okay? And now basically plug and chug. So I chose the first one. So if I want to, do I have rearrange this? Yeah. If I want to rearrange my rate law expression, solving for K, it looks like this. K is equal to the initial rate divided by the molar concentration of the H2O2 raised to the first power, or nothing means raised to the first power. Also in the denominator is the molar concentration of the I minus raised to the first power. And so that's what I mean by plug and chug. You can pick any line and take that last number, that's the initial rate, and then in the denominator plug in the molar concentrations of the hydrogen peroxide and the iodide ion. So just picking on the first row, the first run, that looks like this. By the way, as long as we keep our units, we should get the right units of K. So the rate for that particular run is 1.15 times 10 to the minus 6 moles per liter per second. The initial molar concentration of the H2O2 is 0.010 moles per liter, and that also was the initial molar concentration of iodide, 0.010 moles per liter. So if we let things cancel that are going to cancel, it looks like we have 1 of the moles per liter in the denominator cancel. So this is why our units are liters per mole per second.
Allowing only 2 sig figs, I get 0.012 liters per mole second. That's it. And that's by inspection, and inspection only works if you're doubling the concentration. But it works. So the other one I want to do this afternoon is the algebraic approach. And what I've done in the past is I give students this thing I got off the internet about logs or exponents. And basically what we're going to do is we are going to use the power of logs to get 2 exponents. What is the value of an exponent? We're going to use the power of logs. So for those of you who, like myself, don't deal with it every day, these are some kind of rules of dealing with exponents and logs. Okay, I'm going to do that. Okay, so we have a few tricks we're going to do with this. So now we don't have A and B. I don't know why I changed it up. There must be a reason for it. But now we have 2 reactants, Q and R. Works. I don't know why Q either. Anyway, mine's not to wonder why. So we're going to run it a couple times. So these are 2 different trials. And a few things pop out at you. One is R is held constant, which is good. That makes our life easier. But the other thing about Q is that we're not doubling it. So we can't use kind of by inspection like we did before. So we have to use something else. So I could write, I can't remember how my slides go. Yeah, that's good, I'm glad. I've been telling you, you can write the template kind of for the rate law expression, and it will look like this. Rate is equal to the rate law constant K, rate law constant for this reaction, times the molar concentration of the reactants raised to the reaction order. So if we go molar concentration Q raised to the M, molar concentration R raised to the N. This is the first time I think we're going to do, maybe it's not, but you guys know we can take an equality, and as long as we divide by the same thing on both sides of the equal sign, then it's legit. So all we're doing here, I think we've done this when we talked about the ideal gas law development. All we're doing is we're taking the second run, so we rate 2, do it this way. For the second run, you guys would tell me rate 2 is equal to K times the molar concentration Q2 raised to the M, molar concentration R2 raised to the N. For the first trial, you guys would tell me rate 1 is equal to the same rate law constant K times the molar concentrations of Q and R for the first trial, raised to the same reaction order. You guys would tell me that. So all I'm doing here is dividing both sides by the same thing. I hope this works for you. The reason we're doing that is to ultimately we're trying to get to what M is. We can't get to N for this data that was given, but we can get to M. That's what we're trying to do. Now, the cool thing about both of those trials was R was the same. So here in a minute, you're going to see R goes away. Hasta la vista, R. Okay, because we ran it at the same molar concentrations. We're going to see that K goes away because we ran it. I mean, it's the same thing. So this thing kind of simplifies to this, where the ratio of the second rate to the first rate, now this is our first law of logs, I think, so I'm going to see this on our sheet, is equal to, we're basically going to take the ratio of Q2 to Q1, and then we're going to raise it to the M power. I don't know, this might not be on here. Oh, I guess I'll buy it. Okay, so if you buy that, so we're after M. We're on our way to get M. So the next thing we're going to do is basically, down here you're going to see, we're going to take the log of both sides. The reason for it is if you take, like this third line right here, you want to put a star next to it, where it says log B x raised to the n, that's what we're applying here. If you take the log, it could be the log base 10 like this, or the natural log of anything raised to the power. It's equal to that power, which we're trying to get to, times the log of that quantity. That's exactly it. So we can take the log of both sides, the log of the ratio rate 2 to rate 1, to the log of the ratio of Q2 to Q1, all raised to n power. The cool thing, according to that third law, is we can rewrite this, and that's equal to m times the log of that quantity. And voila, now you have a way to get m. It means you need to dig out your log function, but that's okay, we can do that. So that third row here is exactly what we would like. Now there's different ways, and you'll see on my answer keys, depending upon what kind of mood I'm in. But we need to get to m, so I guess we could divide both sides by what? The log of Q2 to Q1? That would do it. I know it looks messy, but it's right. So to get to the m, it'd be the log of rate 2 over rate 1 divided by the log of Q2 over Q1. And by golly, we have those 4 numbers in that table. We totally have those 4 numbers. No problemo. I think that's where we plug in those 4 numbers. So if you go back and look at them, here's what the 4 numbers look like. Now, you might say, Mrs. Snipes, that's naked numbers, naked numbers. Well, I think my thinking here is I'm taking the ratio of 2 numbers that have the same units. So I don't put my units over here, because yes, I am lazy. So the log of rate 2 to rate 1 looks like this. The log of 0.0104 moles per liter per second divided by 0.00668 moles per liter per second. 6 moles per liter per second, like that. In the denominator, we had the ratio of the molar concentration of Q2 to Q1. So that's 0.212 molar divided by 0.170 molar. So when we're rounding, when you're applying a log function like this in rounding, how does this work? It's like well, I'll say about rounding here in a minute. So you can see what I did is, and it makes sense to kind of simplify before I do my, oh, I know why I did this. There's a reason I did this. Sorry, I'm digressing. So you can take the ratio here, put it there, take the ratio here, put it there. Makes sense. And you get 2. So I started talking about rounding. So maybe there isn't anything big in rounding yet. But I'm pretty sure this is a nice round number, like 2.00000. Now, if you get 1.9999, maybe you're looking at second order. But any questions about this? I thought there was one more trick here, but I guess not. Okay. So that brought us up to where I wanted to be. I'm not sure when we'll finish up this. The last one I want to show you is coming up with reaction orders using graphically. And actually, you guys are going to do that in the lab. Can't remember if this is Thursday or not. I better figure that out before Thursday.